Okay, hi everyone, I'm back. It's been a while since I recorded one of these, but happy to be doing it. This is my first in a series of lectures about the hydrogen atom, described in Atkins 8a. I'd probably tell you that the particle in a box is the most important quantum mechanical model, but this is a close second. Right? It's really the central theme that we get for explaining a lot of chemistry. You're going to know many of the results. Things like SPD orbitals, energy level diagrams, and hopefully you'll get to see where all this stuff comes from. So we're going to start with something, however, which is different and totally wrong. It's called the Bohr model of the atom. This is Niels Bohr. He's like a Danish national hero. And he was working before the dawn of quantum mechanics. So before anyone understood the Schrödinger equation or believed it to be true, Bohr was thinking about the structure of atoms. And what he ended up doing was making some simple but totally unreasonable approximations. And with those approximations, he was able to derive some results which are still meaningful and that we're still going to talk about. So I show it because A, you want to know about these results, and B, I think it's a nice example of how you can start to think about a problem. So what were Bohr's assumptions? Well, the first was that stable orbits exist. So I've got a hydrogen with a nucleus, one proton. There's an electron going around it. That electron experiences both Coulombic attractions, it's being drawn into the nucleus, as well as a centrifugal force, right, from its rotational motion. And he assumed that those were balanced. Right? Now, on the surface of it, this seems reasonable. Right? I could imagine being pulled in, being balanced by the force pushing it out. But if you start to think about it, it kind of falls apart quickly because if anything knocks those forces out of balance, in other words, if that electron interacts with anything in any way, it would either collapse into the nucleus or it would blow out to infinity. And so Bohr didn't concern himself with that. He just said, I'm going to accept that that's true, right? Or believe that it's true. And if that is true, then you can look at your expression for the Coulombic force here, as well as the centrifugal force, and you just set them equal. The second assumption he made was that angular momentum was quantized. So here's our classical formula for J, P cross R. If I solve for the magnitude of that, you get MVR, and he said that was going to be equal to integer values of H bar units. So 0, 1, 2, blah, 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 blah. If you start to put these two together, you get some interesting results. So I can take this original statement, I write this in terms of the angular momentum, MVR. I plug in Bohr's quantized angular momentum, and I get this expression which can be solved for R. Right? I get an R cubed in the denominator here and an R squared. I'll let you do the algebra, but if you do that, here's what you end up with. Right? You end up with this result. And if you look at this in particular, right, what you'll notice is that there's a bunch of constants, 4 pi's, epsilon zeros, h bars, times n squared. And so what Bohr predicted is that stable orbits exist at quantized radii, that the electron was going to exist in these orbits. Now, these constants up front end up being incredibly important moving forward. It's given a name which is called the Bohr radius. And again, you can plug in these values, right? You'll see it has units of length, and specifically it's equal to 0.52 angstroms, right? Or 52.92 picometers. Moving forward, this is going to be the basis for all of our length measurements in quantum mechanics. Right? So that's one important result. Here's the second important result. Bohr was also thinking about energies. So what's the energy of an electron in a hydrogen atom? Well, it has a kinetic energy term, 1/2 mv squared. And then it has this Coulombic attraction to the nucleus, negative E squared over 4 pi epsilon 0 R. Right? Negative because it's being attracted in. Now, Bohr took his previous expression for the balance of the centrifugal and Coulombic forces. He solved this for mv squared and then plugged it in, right? And that leaves you with this, 1/2 times this minus 1 times this gives you negative 1/2 e squared 4 pi epsilon 0 over r. He then took his previous result for r and plugged that into this expression. And if you do all of that and cancel everything, here's what you end up with. E sub n equals a bunch of constants times 1 over n squared. You can also write these constants in terms of h bar squared over m a naught units. Critical thing here is that Bohr is predicting that the energy levels are quantized. So the orbits are quantized and the energy levels are quantized. And in particular, the magnitude of these constants was striking to physicists at the time. So there was a formula known as the Rydberg formula. It is used to explain the wavelengths at which lines show up in the emission spectrum of a hydrogen atom. So you may have seen these before in Gen Chem. They have names like the Balmer series, the Paskin series, the Lyman series, and they show up at these very specific wavelengths. Physicists empirically knew this formula, but they didn't understand where it came from, like physics that described it. And because they empirically knew it, they could run the experiments, and they knew that this Rydberg constant out front had a value of 1.097 times 10 to the 5th reciprocal centimeters. Bohr's formula is exactly consistent with this form, right? You see a 1 over n squared in the denominator. And in particular, when you plug in these constants, you see his predicted value of 1.097 times 10 to the 5th. The physicists were smart enough to say, boy, that's probably not a coincidence, and there's something going on here. And so that's what we'll talk about, right? What's going on is a Schrodinger equation, and we will talk about solving that for the hydrogen atom in the next video. See you then.